Hello, my name is Hyunseok Lee, and I'm a member of the KGSEA Math Circle. And today I'll be doing my open school topic on the topic of game theory and the mathematics of strategy. We'll explore how mathematics can model decision making in strategic interactions, from understanding basic concepts to analyzing real world applications. So firstly, to start with the basics, as in what is game theory? Essentially, in a theoretical sense, it's the study of how and why individuals make decisions about their situations. But to put it into context, we realize that the outcome for a stakeholder in any type of interaction depends on the choices of others or the other stakeholders in that same interaction. So we can basically infer that optimal strategies out of those interactions can be discovered or deduced for groups of individuals. So game theory essentially comes to be as the study of mathematical models and strategic interactions, or an analysis of individual decisions that would pretty much make the best strategy or best decision for an individual or group. So essentially, game theory acts as a navigator in decision making. It's particularly useful when outcomes depend on others' actions. For example, it can model scenarios like auctions, trade negotiations, and even vaccine distribution strategies. By understanding these strategic interactions, we can better predict behaviors or design systems that lead to more favorable outcomes for everyone involved. So to start off, we have a little situation which is pretty much the quintessential example of game theory application. It's called the prisoner's dilemma, and it's actually used in contexts wider than simply just game theory, but it's a very straightforward application of the game theory system. So here, two prisoners, A and B, who are essentially partners in crime, they must decide whether to confess or remain silent without communicating with each other in a trial or an interrogation. So, in this situation, if they both confess, that means that they each get 10 years in prison. If one confesses and the other doesn't, or the other remains silent, the confessor goes free while the silent person gets 20 years in prison. And now, however, if they both remain silent, they get each 5 years in prison. This is essentially a dilemma which highlights how individual rationality can lead to suboptimal group outcomes. And we'll come back to this later, but before we need to analyze what exactly game theory is, as in what is a game, what are the players, what are the strategies, and what are the payoffs. So essentially, a game is refers to any set of circumstances that has a result dependent on the actions of two or more decision makers, in which we call players as decision makers. Players, strategies, and payoffs are the three main terms that we use when representing or describing essentially a game or a situation. So the players are essentially the decision makers, like these two prisoners in the dilemma were. The strategies the strategies refer to the available actions each player can take. For example, a prisoner could confess or a prisoner could remain silent. And now the payoffs are essentially the rewards or the penalties resulting from the combination of the strategies chosen. The rewards or the results or utilities that a player could earn from the selection of strategies that they essentially select. For instance, years of prison time are could be represented as the payoffs in the prisoner's dilemma. So to mathematically notate this, I've noted these down below. P essentially represents the set of the number of players in the game. In this situation, for the prisoner's dilemma, it would be prisoner A and prisoner B. For the strategies, it would be a set of X and Y, which are the number of strategies for SA, which is the number of strategies, the set of strategies for prisoner A, it would be confess or not confess. And the strategy profile is essentially another notation that shows all the combinations of possible strategies for all players. So essentially, for the number of strategies for this particular situation, it would be, for example, confess or don't confess, as an A confesses and B doesn't confess. Confess, confess, which means that A and B both confess, and it goes on and on to represent all the possible combinations that could come out of the situation. The payoffs are essentially represented as one of the one of the sets in the strategy profile. So SI would be SI would represent the strategy that you made, and SI minus I would represent the strategy that the other player made. And this essentially has a numerical value. For example, the numerical value for the prisoner's dilemma would be the number of years you get in prison for the strategy that you chose. For example, the UA or the payoffs for prisoner A when A confesses and B confesses will be 5, which would be 5 years in prison. So when we notate, we use payoff pairs. So a UA and UB, which would be in this situation, if they both confess, it will be 5 and 5 because A gets 5 years in prison and B also gets 5 years in prison. So essentially, this comes in handy when creating a scenarios matrix, which will be used to create the larger payoff matrix. So essentially, it shows the results or the scenarios for each combination of strategies or choices. For A, if they confess, if they don't confess, A and B both get 10 years. If they both confess, if A doesn't confess but B confesses, B gets off free, A gets 20 years, etc., etc. It's the same thing that I showed you in the initial slide. But as you use those notations and tools that I just showed you earlier, as in P would be the set of A and B, the subsets of strategies would be essay, confess, don't confess, the things that we went about earlier. We would get the payoff matrix, which is essentially what's called the backbone of game theory, as it's essentially an evaluation of all the possible choices and strategies and all the utility outcomes, payoffs that each player could get in a situation. As A confesses and B confesses, it'll be -10, which would essentially mean that A gets 10 years in prison, B gets 10 years in prison, and all the other choices are represented in a similar way. So this is a very easy way of showing how game theory would be represented mathematically or in quantitative notation. So essentially this matrix, it comes in handy in that it helps us analyze more strategic interactions systematically. Now, another concept to know is the Nash equilibria or equilibrium, which is essentially the set of choices that players make wherein players can do no better by choosing an alternative strategy. In the prisoner's dilemma, confessing is the Nash equilibrium because if A confesses, then B's best response is to also confess. If B confesses, A's best response is, of course, to also confess. Now, for individual utility or outcome, A not confessing and B confessing would result in the highest individual utility for B, but essentially knowing that A will confess to get a better outcome, then A and B would both choose to confess to get the highest group outcome, and that would represent the Nash equilibrium. So I analyzed the types of games here, and essentially game theory can be divided into a bunch of different criteria. So 4 sets of criteria I did list here. One is either if they're cooperative games or non-cooperative games. So in cooperative games, players can essentially form binding agreements focusing on collective payoffs. For example, they're focusing on coalitions, so they're essentially wanting to get the best outcome for everybody. So for example, trade alliances between countries where players are essentially working together to get the best group output, or joint ventures in businesses to increase profits, where businesses work with each other to make sure that everybody comes out of a situation a winner financially or in terms of profit. Whereas non-cooperative games are where players can form binding agreements or can't form. So they're essentially focusing on getting the best individual output so a bunch of examples would be, for example, auctions where each player wants each better or each player wants to maximize their outcome, not caring about the outcome of the other players. And the one we talked about, the prisoner's dilemma, where A and B are essentially not cooperating with each other. So essentially each player will be each prisoner will be wanting to get the best out of their own. Another example is the zero-sum and non-zero-sum games. So essentially, the zero-sum games means that one player's gain equals another player's loss, hence the title zero-sum, where the total gain and utility would be 0. So essentially, this sparks direct competition, as in, for example, chess, where a win for one player is a loss for another. And for poker, because the pot is fixed and a winning that one player earns comes from another player's or another group of players' collective losses. And for non-zero-sum games, this is where players can have mutual gains or losses and results in the games becoming more collaborative. This is kind of, let's say, parallel to the cooperative games that we talked about earlier. For example, there are trade agreements where all parties essentially benefit and there's not one player or one party to be at loss from another party's gain. And also climate negotiations to reduce emissions, because we're all, in terms of climate negotiation, we're all rooting for everybody's gain without another's loss. Another metric to differentiate the types of games would be simultaneous versus sequential games. In simultaneous games, players make decisions at the same time. So essentially, players don't know when the other no don't know the others' choices when deciding. For example, in rock paper scissors, everybody brings their result at the same time, so one player doesn't know the result of another player's. And pricing competitions where companies decide prices simultaneously because each company doesn't know which other company would result in would bring a cost for their own. So essentially, each company would have to resort to strategies where they don't have to rely on what the competing companies would put out as their costs. Now, in conversely, sequential games mean that players essentially take turns making decisions. So conversely, from simultaneous games, sequential games have decisions that depend on the actions of previous players. So in chess, moves occur one after the other, of course. One player takes a turn and another player takes a turn. And essentially in chess, people make decisions based on the decision that the other player has made previously. Also, in investment decisions, people are making investment decisions with observable stages, such as the market patterns that have been observed in the past. So the final method of separating games would be a cases of perfect information and a case of imperfect information. In the case of perfect information, it refers to a situation where players have full knowledge of all previous moves and game states. For example, chess and tic-tac-toe, kind of like how I explained with the simultaneous or the simultaneous and sequential game. The players have the knowledge of what the previous moves were and what the game state was before, or other extensive form games where all nodes or decisions are visible. The stock market or buying stocks could also apply to this situation as you have all the information about the market and what happened before, basically. So for imperfect information, on the other hand, it would be where some moves or payoffs are hidden from players. Quintessential or typical example of this would be poker, where in poker, people play their cards without knowing what cards that the other players have, or essentially bidding in auctions, like we mentioned before, where players don't know others' valuations and essentially aren't going off of others' decisions, but are going off of essentially their own. Now, the applications of game theory are actually very broad or diverse. Essentially, game theory isn't a mathematical topic as much as it is an economical topic explained by applied mathematics. So game theory is, of course, widely and extensively used in economics, essentially used to understand competition or collaboration between firms when it comes to pricing strategies, where companies use game theory to decide whether to price, let's say, aggressively or cooperatively. In a market with competition, firms must balance profit maximization against the risk of price wars between or against other firms. Um, in politics, game theory is also widely used because game theory is used in those examples that I talked about before, where it's trade agreements where countries strategize, let's say, tariffs and trade terms to maximize national benefits while maintaining international relations, or in voting systems where political parties analyze voter preferences to build coalitions or, let's say, craft policies that appeal to key demographics. In biology, game theory is also used to actually explain evolutionary behavior, to explain survival strategies where predators and prey evolved strategies to maximize their chances of survival, such as, let's say, camouflage or group hunting. And lastly, game theory is also widely used in healthcare and technology as they're used to distribute healthcare or distribute technology. For example, has been widely used or seen as an application of game theory, whereas governments have to strategize how to allocate limited vaccine doses efficiently because in a market, the players, which are, let's say, individual people, have the decision to either vaccinate or not vaccinate. And the other player would be society, where society chooses to vaccinate or not vaccinate. And essentially, those are the applications. In summary, we've talked about what is game theory. We've talked about the starter of the prisoner's dilemma and how it's a quintessential theme of game theory, the key components of game theory, and use that to analyze the prisoner's dilemma specifically, the types of games and the applications of game theory. In further analysis, we would probably use an analysis of the applications that we talked about before, or talk about specific types of games such as NIMS games, which are actually used in questions for competition math such as the AMC. And that was my presentation. Thank you.